Next, for pressure sensor, like this is a typical pressure sensor with the substrate, anchor. And we have pressure coming from the cavity below. So this pressure will deform this diaphragm. Then we are going to use PMOS and NMOS as a pressure sensor in this case. Like PMOS and NMOS. And this one is reference. This one is reference because they are on the substrate, not on the diaphragm. So we have two NMOS will be influenced by the air pressure, and two PMOS will be influenced by the air pressure. And this one is the circuit. We have current mirror 1, current mirror 2. Then Ethan, could you read the first one?
MOSFET is fluence and cell and compressive trace develop in the diaphragm under externally applied pressure and result in the variation of their carry mobility.
Okay, thank you. See, if we have air pressure, then this one is under here, this one under tension or compression?
Tension.
Pressure.
Compression.
So this one, remember, if the bending goes this way, here is expansion, here is compression. So this one is compression, but this one is in tension. See, pressure goes here, here is compressed, but here is expand. So we have tension, compression. The same here. Muscle. So if we have pressure coming from below, so this one under tension or compression.
Lower side should be compression and upper layer should be in tension.
This one, tension. And this one? Like this one, tension or compression.
Tension. So the possible upper is tension.
So here, this one, tension or compression.
Impossible. Compression impossible.
Pressure coming this way. So this one,
Yeah, compression.
compression, and this one is tension. The carrier mobility will be influenced by the tensile and compressive stress. So this is the property we are going to use to design this pressure sensor. So Ahwan, could you read the second one?
Orientation in carrier mobility results in the combination of current and voltage of MOS.
Okay, for transistor. So if you don't know about transistor, just imagine we have current going through from top, going down. We have current from top, goes down. Then we call this one gate. We call this one source. We call this one drain. D-R-A-I-N. Source, gate. So we have current coming from drain to the source. So this is the current. Frank, what's the name of this one? We have 3 points. What's the name of this point? gate, drain, source. Pick one. Drain, correct. Leo, what is this point? Source. We have gate. Then the carrier mobility. Remember, voltage equal to current times resistivity. So if the carrier mobility changes, then current changes, then the current changes. So the voltage, the chain reaction, mobility change, current change, then voltage change. Okay. Kumel, could you read the third one?
An output voltage proportional to externally applied pressure is obtained across the drain terminal of pressure sensing MOSFETs MP2 or MN2 and MP3 or MP3.
Okay, because MN1 and MP1 are not influenced by pressure, so there's no tension, there's no compression. But MN2, MN3, MP2, MP3, they are influenced by this pressure. Their mobility will be influenced by either tension or compression. So the output voltage will be proportional to the pressure. See, we have output voltage. So this voltage output will be influenced by this pressure. Fatigue. So do you have any problem here? Any question? No? Okay, next page. So the pressure could be either coming from below or coming from the top. Depends on your application. Then fatigue, could you read the first one? The first point.
Under applied pressure, maximum displacement occurs at the center of the diaphragm. Maximum positive tensile stresses are developed at the mid of the fixed edges of the diaphragm, and maximum negative compressive stress is developed at the center of the diaphragm.
Okay, if now the pressure comes from the top, so we have tension here, we have compression here. Comes from the top, you can imagine this one goes down. So this one is under expansion, but this one is under compression. Frank, so do you agree?
Yes.
Okay, very good. Kaiser, could you read this one?
MOSFETs MN2 and MN3 experience positive tensile and negative compressive stresses respectively.
Slowly.
Develop in the
One word by word. Once again. Stop.
MOSFETs MN2 and MN3 experience positive tensile and negative compressive stresses respectively develop in diaphragm 1 under applied pressure.
Okay, diaphragm 1, we say this one. Diaphragm 1 and diaphragm 2. So remember, this is not shuttle mass, this is substrate. Substrate, anchor, and anchor. So we have two cavities. Okay, so far, any question? Sorry, Frank's friend, what's your name? Stephen. Let me ask you again. Under external pressure from the top, so for this MOS, Is it under tension or compression? Tension or compression? Huh? Just guess. Compression. You are wrong. Tension. See, if you bend this way, so here will be tension, here will be compression, bending down. So this one, center will be compression, and here will be tension. Can you imagine? Okay, next. Then, now is for this case, diaphragm 2. So I would like to have Aga, could you read this?
Force FET, P2 and P3. Expressions force positive and negative forces, stress is expressly involved in
Diaphragm.
diagram 2.
Okay, so we want to do some experiment. So here, could you bring that pile of paper? Yes. Okay. So anchor. Pressure from the top. On the top. So here is compression. So here should be tension. Just do some experiment. Thank you. Okay, next page. Then we got a simple equation for this sensor. The drain to source current, IDS. So this one is the mobility of the electrons or holes in semiconductor transistors. And this one is the width. So like just imagine a capacitor. We had previous. So just imagine we had, so this one, we had length L, we had width W for transistor. So the length L and width W will influence the current. So electron goes this way and holes goes this way. So you can imagine current goes this way. So D, drain, source, gate. So the current IDS is influenced by the mobility mu, the length L, and the length L, width W. Okay. Next. And VGS is the voltage you applied between previous. This is gate, this is source. Okay, next. And VT, just a constant, a voltage. You need to, for VGS greater than VT, your device can work. Otherwise, there's no current, it's off. So this is the equation we are going to use. And this one is the resistance of the between drain and source. The resistance. So this is resistance between drain and source equal VA divided by IDS. You can treat VA as applied voltage. Okay, so Boston, could you read this?
Where micro is
Mu,
mu is the
mu, mu, mu.
mu is the carrier mobility channel region.
CX.
CX is the outside capacitor per unit ion. W is the channel width. L is the channel length. VGS is the gate to source voltage. VT is the threshold voltage. RO is the output resistance, and VA is early voltage edge of the MOSFET.
Okay, so if you feel a little bit confused, it's okay, because if you have not learned this electronics, you won't be too clear, but you can spend some time to read the fundamentals, or you can ask some electrical engineers. That could help you to get more understanding of this terminology. Okay, next page. Then, yeah, the channel resistance here between the drain and source. So this is NMOS, this is PMOS. So we have resistance R0. And in this case, because we mentioned R0 will be influenced by pressure, and pressure is stress. So if the resistance can be changed by stress, that is piezo resistor. So we can model this effect as piezo resistor, RO. So you can take this one, is similar to a piezo resistor, because just what we know, pressure change mobility, and mobility change current. Then current change means we have resistance change. Okay, anyway. So RO is the channel resistance. Ming, could you read this one?
Relative change in MOSFET drain current under applied mechanical stress solely depend on stress-induced carrier mobility ratio. Therefore, the relative change in carrier mobility of MOSFET under applied pressure.
Okay, good, thank you. Remember, R change, mobility, because mobility change means R change, but R change, because they are due to pressure stress. So remember this equation, delta R divided by R equal to minus pi sigma. So you can ignore this minus sign. If you ignore the minus sign, this one is piezo resistor. Okay, so next. For PMOS and NMOS, the pi value. Yeah, we calculate these equation, these values in our previous lectures, but they are useful for later. You will use simulation software, so you need these values, because for mechanical engineer, they apply pressure, they calculate the stress. The stress times these coefficients, previous. See, stress multiplied by the pi values, we can get resistance change. So we need pi values of PMOS and NMOS. Next. For this case, we have six. We have three PMOS and three NMOS. And NP1, MN1, they are fixed to the substrate. So, see, NP1, MN1 unstressed. So unchanged because they are fixed. They are not influenced by tension or compression. NP2 and MN2, they are at the edge of the diaphragm. So under tension and under the pressure stress, so if we have the pressure from the top, then this one is tension. Then product pi sigma. Remember, we need a pi value previous. Okay. For PMOS, if we focus on pi 11 because it's bending in one, we take the pi 11 is more important than pi 12 and pi 44. So PMOS negative, NMOS positive. Next. PMOS pi negative times positive, negative. For NMOS, pi value is positive. So positive times positive is positive. Okay. So the channel resistance, previous. See the channel resistance. So if this is just minus, they can be ignored. So positive increase. Okay, next. Okay, positive. So this one increase, this one decrease. But mobility, previous. See, we have this is positive, this is negative. So resistance increase, mobility decrease due to this negative relation. Next, see, increase, decrease, increase. So you can use your mental experiment to go through the same process. The same, you'll get the relation. Okay, next. Then is the circuit, the equation. Lai, could you read the first point?
A dual current mirror phase CMOS readout circuit consisting of three identical B-channel MOSFET and three identical N-channel MOSFET.
Yeah, so for the three PMOS and three NMOS, they are identical, the same arrow, the same dotted. Then we can use the same equation for this one. So this one is the relation between these values. So we are going to use these three equations for simulation of our device. Gan, could you read this?
VDD is the supply voltage. V in and VTO and VTP are the threshold voltage for NMOS and PMOS. VGS1 is the gate to source voltage. VDSN1 are the drain to source voltage. U1 and
UN1, UN2, UN3.
U1, 2, 3 and UP1, 2, 3 are the electrical and hole mobility of
Corresponding.
corresponding most FET MM 1, 2, 3 and MP 1, 2, 3.
See, we take VDS1 and VGS1, we take them equal to each other. And previous. Okay. So for VGS1 and VDS1C, they are connected. So see, they are connected. So VGS1 and VDS1, because VD and VG are equal. So, Frank, do you follow me? Yeah. Okay, go to the page. So that's why we have this. And for the derivation of this one, you don't need to derive by yourself. We just take the equation. Then VDS2 and VDSN3, we can follow the equations for our design. Next. Okay. Then see, this is output voltage. VDSN2. So this is N2, DSN2, DSN2. This is ground. VDSN3. So VDSN3 is the voltage here. VDSN2 is the voltage here. So V out equal to the difference between this point and this point. V out. Kumel, could you read this?
The output voltage proportional to externally applied input pressure is measured across the common drain terminals of pressure sensing MOSFETs, MP2 and MN2, and MP3 and MN3 respectively.
Okay, yes. So yeah, this is clear. V out here between MP2, MN2, this point. Between MP3, MN3, this point. The difference between these two voltages R is the V out we take from this sensing circuit. Okay, next. Okay, so remember MP1 and MN1, they are under substrates, so they are not influenced by the external pressure. Only this area will be influenced by external pressure. Bill, could you read this?
Under zero applied pressures condition, mu P2
Okay.
equal mu P3, mu N2 equal mu N3, VDSN2 equal mu DSN3. The output voltage of the sensor is 0. V out equal 0 under applied pressures. There will be variations in the carrier mobility of pressure sensing. MOSFET, MP2, MP3, MM2, and MM3 such that mu P2 not equal mu P3 and mu N2 not equal to mu N3 as shown in table 2. This will result in VDSN2 not equal to VDSN3. Hence, producing in non-zero output voltage corresponding to the input applied pressures.
Okay, thank you. Remember, P2, P3, one is tension, one is compression. and N2, N3, one is tension, one is compression. So they must be different. So if you have these two conditions, previous, okay, see, we have N1 at mu. So we have the mu value here. So using the equations, you will have different VDS N2. Okay, next, previous. Okay, VDS N2, VDS N3 will be different. So you can use the equations for calculation. Next, so you are going to use LOT SPICE to do the simulation for this case. So LOT SPICE can simulate the circuit. And because we have several electrical engineers, so they will be able to help mechanical engineer for LOT SPICE. We have 1, 2, 3, 4, 5, 6. We have 6 electrical engineers. We have 1, 2, 3, 4, 5, 6, 7. So you count you as a mechanical.
Precision.
Physics.
Precision.
The background,
Your background.
Yeah.
the university.
I mean your major
Mechanical.
or mechanical. And you are electrical. Mechanical. Huh? Electrical. Okay, so we have even number. We have 7 electrical and 7 mechanical. Okay, so each mechanical and each electrical will become a team and work together for the LOT SPICE. So the voltage applied, the early voltage. So, okay, so Adam, could you read this?
The voltage equal to the early voltage of the channel, and the channel most VT is applied across the both and the most in.
Okay, yeah, previous. Okay, we have this equivalent circuit. So we have the early voltage, VA, for the equivalent circuit. Okay, next. Next one. For this one, apply pressure and the delta R. So this is R value. So this is P. We use finite element analysis to get this relation. But we are not going to do finite element analysis in this case. So suppose you have this table, you have this video. So you can use the number here for LOT SPICE simulation. Then the initial resistance. Okay, Amin, could you read this?
The initial channel resistance of PMOS and NMOS equivalent piezoresistor and found to be above 79.60 ohm and about 237 and 78 k ohm respectively.
Okay, thank you. For PMOS, so initial resistance is 79.16 k Next, for NMOS, the initial resistance 237.38 k. So this is the relation between pressure and the resistance change. So these two figures, you will use them for your simulation. You need to estimate. You can say, you can draw some grid, or you can use MATLAB for image processing. You can use MATLAB, or you can use any computer software, or just use hand drawing several lines to estimate their values for your simulation. Next. Ming, could you read this?
The carrier mobility for P minus and N minus channels most activity under no load condition are 250 cm to VS and 750 cm to VS respectively.
Okay, so this you also need the mobility as function of the pressure. So for each pressure, you will have the mobility value and the resistance value for you to run your simulation. LT-SPICE is a free software you can download from Analog Devices website. But you may need to know how to model the transistor. So you may take some time to learn how to do that. They have tutorial how to create a transistor in LT-SPICE. So you should be able to work it out by yourselves. Okay, next. Okay, the mobility for NMOS. See the initial one, 750 cm squared per volt. Okay, next. Stephen, could you read this? Thank you. So you have resistance variation, mobility variation as functions of the pressure as your input to the LT-SPICE. Next. Then each team, we have 7 teams. You are going to plot this figure, drain current as a function of the applied pressure based on LT-SPICE. So, Marcel, could you read this?
Variation in currents and voltage at the common drain terminals of MP1 node 1, MP2 node 2, and MP3 node 3 as a function of applied pressure. Okay, so we will have 5 minutes break. So during the break, please, you need to find your team member. We have 7 teams. So let me know each team, the members of each team. Then we'll go from there. Okay, so I'll see you in 5 minutes. To use in your SPICE model. And the early voltage, VA, is 1 over lambda, early voltage. So they give you the early voltage. So
now is 206. In our lab, we have 8 computers. So you can work in our lab, because you could ask. We can watch them doing it. And LT Spice is free. You can just download LT Spice from internet. Okay, so